Okay, welcome back with another video of equivalent series. Today we will be see how equivalent resistance is solved. Right? Okay, again, if I quickly recall, equivalent is a single unit to replace a system. Right? When it comes to resistors, a resistor functions with Ohm's law, V equals IR. Right? What is Ohm's law? Ohm's law, V equals IR. Right? Where V is potential difference, not the potential. This is potential difference. Potential difference. I electric current. I electric current. R resistance. Right? This is called Ohm's law. V equals IR, Ohm's law. Right? Now, let's see what the series combination of resistance is. Right? In series combination, we know end-to-end connection should be done in series combination. In previous videos also I explained. In series combination, if there is a series combination, it should be end-to-end connections. Series, right? Series combination, let's say. Series combination, right? Should be a series connection, end-to-end connection. See, now let's consider these three resistors which are connected end-to-end like this, right? And their resistances are R1, R2, and R3, right? And they are connected between A and B, let's say, points A and B. They are connected between points A and B. Right. Now, if a current I comes from here, see, if a current I comes from here, if a current I flows from here, if there are no junctions, current is not going to be divided. If there are no junctions, current is not going to be divided. Simple as that. Therefore, same I flows through all resistors. Same I flows through all resistors. Now, we know equivalent is a single resistor to replace this system. Equivalent is a single resistor to replace the system. If this system is between A and B, equivalent should also be between A and B. Right? If this system carries a current I, this equivalent should also carry the same current I. Right? Let's consider this resistance as Re. Right? Now, according to V equals IR, see, according to V equals IR, now currents are same in the given scenario. When resistances are different, then voltage difference should be different. But the point, voltage difference should be different. So therefore, voltage difference across each resistor is going to be different now. Let's say voltage difference across the first resistor is V1 and voltage difference across the second resistor is V2 and the last one is V3, right? And total voltage difference across the system is it is connected between A and B. No? It is VAB. It is VAB. Then that same VAB is across the equivalent here, VAB, right? Always when you are developing equivalent equations, develop the argument based on the different physical quantity. Now, different physical quantity is voltage difference, potential difference. So, build up the argument with the potential difference. VAB should be, this is the argument. VAB should be, now VAB is divided into 3 here. Therefore, VAB should be V1 plus V2 plus V3. VAB equals V1 plus V2 plus V3. Right? We know V equals IR. Therefore, VAB can be written as IRE, isn't it? V1 can be written as IR1. IR1. V2 is IR2 and V3 is IR3. I2, 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 I cancels. RE comes as R1 plus R2 plus R3. Right? So this is the equation for equivalent resistance in series combination, and this equation is also valid for any number of resistors which are in series combination. There is just an addition. So therefore, higher the number of resistors in series combination, higher the equivalent resistance. Higher equivalent resistance means it lowers the current flow. Higher resistance means lowers current flow, because electric current and resistance are two inverse things. Right? So this is what happens in series combination. Now let's see what happens in parallel combination. Next one, parallel combination. Parallel. Parallel combination. So we know parallel combination is a same and together combination. Parallel combination is a same and together combination. Right? All same side ends should be together. All same side ends should be together. Right? Such combination is called a parallel combination. Right? All the points should be connected with the same point together. Right? Now, let's consider these three resistors which are in parallel combination. See, these three resistors, these three. See, now say this side is A, this point is B. See, connect ends are together. Ends are together. All left ends are connected to A, all right ends are connected to right terminals are connected to B. Ends are together. Such combination is a parallel combination, and especially in current electricity, if same current flows, there is a series combination. Right? That is how series combination can be identified in current electricity. If same current flows, if same potential difference acts across, such connection is called a parallel connection, parallel combination. Right? See, say this one is R1, this is R2, and this is R3. And equivalent should also be between A and B, same points. Right? Should also be between A and B, let's say RE. Right? Now, if there are no electronic devices met, points of a circuit remains same, which means if this is A, no electronic devices up to here, that is A. This is also A, same wire. This is also A, same wire, no devices. But after this side, after this device, this resistor, there is not A. Check from the other side. If this is B, this is B. This is also B, this is also B. Right? Now, according to V equals IR again, now potential differences are same. But when R is different, definitely current flow should be different. When R is different, current flow should be different according to the equation. Therefore, now I'll consider the current comes into the system as capital I. Current flows are different, no? Let's consider current flows through 1 as I1, 2 as I2, 3 as I3. For the system comes in current should go out, current inflow and current outflow should be equal according to Kirchhoff's laws. So that is same I, right? Then here also, whatever happens for the system should be happen through the equivalent single-handedly. Then same I current, capital I current should flow through the equivalent resistor, right? Now different one is what? Different one is current. So build up the argument based on current flow. What we can say is capital I should be simple I1 plus I2 plus I3. Current inflows and current outflows of a junction should be equal. Current inflows to a junction should be equal to outflow of current from the junction, right? Kirchhoff's first law, right? Then we know V equals IR. Now from here, V equals IR, which means I is VOR. No? I is VOR. So from this, plug these values for I. Then for this one, it should be VAB over RE. For I1, same VAB over R1. For I2, VAB over R2. For I3, VAB over R3. VAB cancels. So answer is here 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. Right? So this is the proved equation for equivalent resistance in parallel combination of resistors. Right? That's a 1 over addition. Therefore, higher the number of resistors in parallel combination, it lowers the equivalent resistance. When equivalent resistance is lowered, current of the circuit increases. Right? Okay. So I hope it's clear. I'm going to stop the video here. See you all in another video of equivalent series. Goodbye.